All right, hello everyone. My name is Matt Halley. I'm a sales engineer at Buckley Associates. I'm also the sustainability chair at the ASHRAE Boston chapter. I'm going to introduce our speaker, Leonard Stahl. He's a 35-year senior engineer from multiple parts of the industry involving refrigerant. Go ahead, Leonard.
Thank you, Matt. So my name is Leonard Stahl, and the purpose of this presentation is to try to give you guys a better understanding of the regulatory framework, risk mitigation strategies, and compliance pathways outlined in the standards. I'm going to talk about these three standards, but we have limited time, so it's going to be the most important pieces of that. The agenda for the presentation is this: an overview of the standards, talk about the fundamental design steps, and then determining whether you apply which standard you use, when and why. And then we're going to look into the 15.2, verify compliance, go through the basic steps in that one, take a step back, do the same thing for standard 15. And then at the end of this presentation, look at actions if a system doesn't comply. And then the takeaway slide at the end. And if you want PDH credits for this, this is worth 1 PDH credit. You need to, in the chat box, put in PDH. And then you have to wait until the last slide also. But put in PDH that you want that in the chat, and then we're going to make sure you get your certificates. So as I see it, these three standards, 15, 15.2, and 34, it's a lot of confusing information in it, to be honest. It kind of spread out in many places. They're not really structured for an engineer to use or someone to use them. It's spread out. But someone have said that the standards, unfortunately, are subject to differing interpretations, and that's unfortunate. But to me, it's like a jungle, but I'm kind of trying to clear it up a little and see where the light is in this. You can see an ugly formula in the top there. We're going to discuss that one at the end of this presentation and a few other things. So we talk about three standards. For 100 years or so, from 1919 to 3-4 years ago, it was only two standards, standard 15 and standard 34. Then 2022, ASHRAE did a major rehaul of these and came out with a separate standard for residential. That's called 15.2. It's 86 pages. So then we had total of 200 pages of standards plus another 200 pages of addendas. And I'm coming back to addendas, but they are very important in this. We're going to see that in a few slides. End of last year, ASHRAE reworked it again. So then they came out with the 2024 edition, which is unusual. Typically, they try to do it every 3 years. Now they did it after 2 years. The good thing is that they put in all the addenda information into these standards. So by end of last year, it was 3 standards, no addendas. Well, now it's another 10 months or so into this year, so new addendas are coming out. And addendas are important because if you read one of these standards, great. But if you haven't checked the latest addendas, you might not have the correct information. One sentence in one of these addendas can change a lot in the standard. Addendas are issued for corrections, clarifications, or changes by ASHRAE on an as-needed basis. We need to remember that these standards are application-based standards. They're not really equipment design guides. Obviously, when we design Fujitsu equipment, we follow the standards, but at the end of the day, it is how you apply these products in the field that is controlled by these standards. There's a code adoption process also. These standards are just a document issued by ASHRAE, but then it's going into an IMC or some other model codes and then trickle down to city or state code. So it's a step, there are several steps, and it can take years sometimes less, and sometimes even more. But when it's more important, like now with the new A2L refrigerants, it's going to go faster. So if you want to know what's going on where you are, I clicked on, this is a map, I clicked on Dallas. This is available from AHRAE, and you have a QR code if you want to go to that site, but you can go to that site, clicked on Texas, and then out on the left, it might be hard to see, but there you can see, click on with further links and kind of trickle down to Austin or Houston or certain parts of Texas regarding the codes that are applied right there, have turned into be local codes. The updates has been a lot of updates, as I mentioned earlier, but as of today, we have another 17 addendas out there. And one of them is very important. I'm coming back to that. Some addendas aren't that important, but there are a few that are really important. And this is, I bet you, if I look at this slide in a couple of months, it's going to be 20 addendas because they work on those constantly. People say mildly flammable or flammable. That kind of can be concerning sometimes. These are called mildly flammable refrigerants, these A2Ls. But we need to remember a few things around that. If you look at the right, you can see the classification in that table from ASHRAE. In the middle there, we have in red R32 and R454B. They are called mildly flammable and with low burning velocity. If you go out to the right, the toxicity is going to increase. If you go up in that table, the flammability goes up. And that's why you have propane at the top, because that's very flammable. 14A that we're using now, it's down in the left corner. It's a low toxicity and low flammability, no flammability, but it has a high GWP, and that is why we can't use it anymore. So for this A2L to ignite, it is at least 4 conditions that's needed. There needs to be a certain concentration between the lower and the upper flammability limits. And there also be sufficient ignition energy, enough for it to ignite. Cigarettes, toasters, and regular appliance heaters don't do it. Need to be high temperature. For 454B, it needs to be at least 925 degrees Fahrenheit. For R32, 1190 degrees. So that's telling me that if the temperature goes up, 454B is going to ignite earlier than R32. We did to use R32 for many reasons, but that's one of them. For this to ignite, you also need a constant oxygen supply. These A2Ls have very slow burning velocity. They burn with about 0.15 miles per hour. Compare that with 3 miles per hour, that is the walking speed. So you can walk 20 times faster than this would spread. Actually, if you Google crawl space, it's going to be 0.3. So you're going to be able to crawl twice as fast as this can spread. There is no perfect 14A alternative out there. It has to find something that's a compromise, a balance between GWP, ODP, and also efficiency, capacity, availability, and cost. You can see the list there on the left, what needs to be considered here, and R32 is really good for all these, but one item where it stands out is the bottom one. It's a single component, makes it easy to handle. I listed below there those 7 or 8 that are approved right now by EPA to be used, and they are all blends. R32 is a single component, going to make it easy to handle in so many cases. It also seems that when GWP goes down, flammability goes up. That's why it is this concern now with these A2Ls. So let's look at the timing for this. Right now we are at later part of 25. In gray we have the years horizontal there, and then upper part, the yellow, is for systems below 65,000 BTUs. They have to, if they are non-A2Ls, they have to be manufactured or imported by January 1st this year. So they have to be done, can be in the warehouse or so, and then there is a sell-through for at least a year. So those that were manufactured or imported by early this year can still be installed during this year. There are some work going on there, so it might be an extended sell-through, put the installed there, but it might be extended. But as of today, it has to be done by the end of this year for those non-A2Ls below 65,000 BTU. For bigger systems, VRF basically, it's similar but delayed. Above 65,000 BTUs, it has to be manufactured or imported by January 1st, 2026. So it's a couple of months left. And then there is a sell-through of either 1 year or 2 years, depending on when that system was permitted. So that is the kind of the background and why we are where we are right now. There are some fundamental design steps in applying these standards. I see at least 4 on a high level. You have to develop a preliminary layout of the system. If it's a VRF, it can be a little cumbersome perhaps. If it's a mini split, it's easier. You have to determine the amount of refrigerant in the system and then verify if it complies either with 15.2 or standard 15. You have to pick one of them. And then if it doesn't comply, there are actions you can take. We're going to come back to that. Very important here in this discussion is the ASHRAE, authority having jurisdiction. That person or that organization is the one that sign off of this. So it's good to have a close contact with that function. So to do a design layout, you would use, if it's a VRF, I would use a design software. Fujitsu's is called Design Simulator, really user-friendly, and you get a lot of output. You put in the layout, you lay out your system, and then you get the charge, bill of materials, pipe sizing, your capacity ratios, all that information is shown. And then if you then can just look there in that output, and you can see the refrigerant charge. And that's very important for the discussion we're having today. How many pounds of refrigerant it is in that system. So we have done those 2 high-level steps, A and B. Design step 3 is to verify which standard to use. 15.2 says it's important to look at the definition of standard 15.2 because it decides what's not being standard 15. So 15.2 is used in residential applications, single dwelling or unit or sleeping unit, 1 and 2 family dwellings and townhouses, individual dwelling units and sleeping units in the multifamily dwelling. So that is the definition on that level of when to use standard 15.2. Standard 15 is very simple. It says that if you don't use 15.2, you use standard 15. So if you have some kind of application that doesn't apply to standard 15.2, use standard 15. So let's take a look at standard 15.2 first. We go back to sub-steps, a little more detailed steps. We're going to determine the refrigerant charge. We call it MS. I'm using the same abbreviations as the standards. Sometimes they are not that good, I think, but let's use those just to be consistent. So we have a system charge, we already did that. Then we have to determine dispersal floor area. It's not necessarily the same as the floor area, but dispersal floor area, coming back to that. Same with the height, determine the dispersal height. And then you have...
Hey, Lennart. Hey,
yes.
Lennart, you have a lunch reminder on your screen right now.
Oh, that's not good. Sorry, yeah, I wouldn't mind lunch, but let's continue.
Sorry about that. Yeah.
Thank you. Anyhow, so and then when we have that information about it, we can determine the M max. That's a maximum allowable charge. And then when that's done, we compare that with the MREL, that is the system charge. And then we see if we comply or not. So this standard, it's a lot of tables, text, logics, flow charts and things. And I'm going to simplify it, which I can do because we're using heat pumps. We're not doing chillers or anything else. We're using A2L refrigerants. So one of those charts, we can look at this one. It starts in the left corner there, trickle down through that flow chart, and then eventually we come into that red block. It says a system refrigerant charge MS less than M1. Well, what is M1? That is in a table. You can look on the right in red. There is M1. That's a charge level. For R32, it's 4 pounds. It's similar for the other refrigerants. If you go down there, 454B, the same, 4 pounds. So that's a one charge level. The question in red is the charge you have less than M1? If it's yes, you go to the right. Charging is in compliance. You're good to go. Less than 4 pounds in the residential application, you're good to go. If it's not, then you go down, it's a no, and then another question in blue says, is the charge bigger than M2? What's M2? I go back to my table in blue and see that's 35 for R32. 454B is 33.9. So if it's above that, those numbers, then we go out to the right and say if the charge is unacceptable. Those numbers are kind of similar, but if I have a system of 34 pounds, I can still use R32, but I cannot use 454B because the maximum there is 33.9. So it's a small difference, but it could be significant if you are right there in that those numbers. So if we are between the 4 and the 35 in this case, then we have to go down and look a little closer at the heights and the size of this room. So the dispersal floor area, that is the area that's served by an indoor unit. You always look at the smallest room floor area of any space, which makes sense because that's going to be the worst case if you have a leak, and that's where the concentration is going to be highest. They also talk about connected spaces in this standard, which is good because even in the old standard, it said connected spaces, but they didn't define it. It wasn't defined what a connected space was between two rooms. You could have connection between two rooms. You just said if they're connected, great, but it didn't say what. This new standard is much better. It talks about what the connected spaces are. On the left, you can see if we have one unit into a room, that is that room. That's the room area you use in your calculation. If I, in the next over there, have two rooms, A and B, little different sizes, and ducted to one indoor unit, and I don't have a refrigerant detection system, then I have to use the smallest room, which would be room B in that case. I'm going to call it refrigerant detection systems. Sometimes in the standards, they call it leak detection systems. It's kind of the same thing, at least for the purpose of this discussion, but there's a slight difference. Unfortunately, they're not consistent in these standards in some cases. Next one over, if I have a refrigerant detection system, I can use both of those rooms. I use room A plus room B. That's going to change the possibility for us to use this system. Over on the right, they also talk about connected spaces. If they are adjacent to each other, you can have room A and room B, and they can be next to each other. Can they be connected in between? They can, actually. The standards specifically say on the left that we cannot have transfer grills or undercuts. We cannot have it. Doesn't address height or size or anything. You cannot have it. But it says that, this is standard 15.2 obviously, but it says that you can have passageways in between two rooms, and it defines it as being same floor, permanent opening, doesn't have a door because doors can be closed, so don't have a door, and it has to go all the way down to the floor and intended for people to walk through. So then you can imagine the size of that opening. It's going to be kind of a door frame kind of thing. Then they are connected. If they are connected with that kind of passageway, then you can use both those rooms in the volume calculation. So that is for the area. Let's look at the height. If we have suspended ceilings, on the left, you can see we have a suspended ceiling with a ducted unit above. We cannot use or include the area above that suspended ceiling. But if we take out the supply or return duct from that unit, then we have connection with that space above the suspended ceiling. We can include that in the volume or in the area calculation. But it can't be more than 9 feet. It doesn't allow to be more than 9 feet, that dispersal height. So the standard says that for ducted system, it has to be the mean of the ceiling heights in the spaces. Can never be more than 9 feet. That's for ducted systems. For ductless systems, it has to be the height of the lowest point of the equipment opening delivering conditioned air. but it can't be less than 2 or more than 9. So it's a range there, but that's for the opening delivering condition there. On the left, I put in 3 units. I have a floor unit, but even if that floor unit is pushing out air at the floor, it has to be at least 2 feet in my calculation. Over on the right, I put only one wall unit really high up, 10 feet. Well, we cannot use more than 9 feet of that for the dispersal height. So that's what I meant earlier when I said dispersal height and area is not always the same as the room height and the room area. So we determine the height and the volume, and then let's see how much we can allow for standard 15.2. It's 2 formulas in the standard. I put them in there. One, it talks about a system without ventilation, the top one. M max, that's a maximum allowed. How much you can allow in that case is a constant C times M, 2 table values. It's straightforward. You multiply C and M. M is from a table, then you know what the maximum is if you have no ventilation. Ventilation in this case is ventilation for dilution of, so you bring in fresh air basically for dilution of a leak. If you have ventilation, we go to the one below, same thing. M max is the same as constant, multiply with M, and now we have MV, which is an additional number because we have ventilation. So let's take a look at those tables. This is the C factor, straight from a table. R32 is 1. So you can kind of see when they developed these standards, they looked at R32 and then they added a few. 454B has 0.96. And since that formula was a multiplication, it's telling me that 454B would allow a few percent less than an R32 system based on that. So that was the C, that factor. I can go into the table and determine the M, the maximum amount. On the left, you have the area in square feet. In the column, I go down to 300. In yellow, I go out to the right. I stop where the red is. That's 20.7 pounds if I have a system with circulation. Circulation is interesting because it doesn't really specify what circulation is. But it's circulating air, most likely from the equipment running the fans in the indoor unit. That would be circulation. I wouldn't think that putting a floor fan somewhere would be considered circulation, but the fans in the equipment should be that. If I don't have circulation, I go out a little further to the right and end up at 14.6. That is for the M factor without circulation. And this is for 7.2 feet dispersal height. If you have other heights or other areas, you just interpolate or use closest lower value. So this is for kind of an average room. So that was the factor M in the previous formula. Let's look at the MV. That's the additional factor if we have ventilation. Then the room height and size doesn't really matter. Then it's ventilation rate, the CFM. Go down on the left, hit 160. In this example, the table goes much further. I just made it simple at 160. And I go out to the right. If I have circulation, I can add 5.6 pounds to the previous number I had. If I have no circulation, it's going to be half, 2.8 pounds into that formula. So you can see that ventilation would help you in this case. Could be 5 pounds at least, even more if you have more CFM. Then to determine MREL, they call it MREL, which can be the same as MS, the system charge that we looked at earlier. Most likely in residential systems, you don't have this, but you could put in shut-off valves, solenoid valves basically, somewhere in the circuit. That would shut off in case you have a leak. Then only a part of that circuit would leak out, and that could be a way to limit the amount that would leak out. So now we have discussed how you calculate the max, what the actual system charge is. So let's see if we comply. Let's look at the charge first. If MREL, the amount you have in the system, is below M max, then we comply. Then we're good. And you remember those formulas, I put them in there. There are two different ways to look at it, with and without ventilation, with and without circulation. So that is, just compare those two numbers. If you comply with the charge, great, but then do we need a leak detection system? And there are a few things to think about there. If MS, the system charge, is less than 4 for R32, we don't need LDS. If it is above 35, as we looked at earlier, then it don't comply, so it's irrelevant whether you use LDS or not. You can't use that system in the residential. And then if it's between those 4 and 35, you would need an LDS. If you use it to operate any shutoff valves, if you have those to shut off a part of the circuit, they need to close when you have a leak, so that would be initiated by the LDS. If you have air circulation, that kicks in case of a leak, or if you run it constantly, then you don't need to trigger it with an LDS in case of a leak. Same with ventilation. You can start it with the LDS in case of a leak, or you can run it constantly. So LDS should typically not be required in residential systems. And then also if you use have several connected spaces, then you need an LDS as well. So that is the requirement for charge, whether we need a leak detection system or not. And then that leak detection system, the standards specify it. They need to have a set point that can't be adjusted. It has to have self-calibration. It has to allow component replacement, probably for the sensor itself, the sensor part of it. We'll probably replace the whole unit, but there is a sensing element that you could replace. It must have self-diagnostics. And if that self-diagnostic fails, you need to start air and ventilation fans. It's described in there also. And it has to be a delay of 30, it can't be more than 30 seconds before that happens. So that's what the detection system has to comply with. If you have an alarm situation, start the fans, open any zoning dampers. If you have dampers in the ductwork, you open those, activate ventilation, shut off duct heaters unless there is a proven airflow function, or you have an airflow that exceeds 200 foot per minute. And then, of course, close those safety shut-off valves as well. So that is the leak detection system. Piping system requirements. This is a very short, it's several pages in the standard. But in general, the piping need to be protected from corrosion and mechanical impact, of course. Has to be at least 7 foot 3 inches or more above the finished floor. Unless it's very close to an appliance, then you can have it lower. Piping shall not be installed in exit corridors, etc., passageways. The word exposed is interesting there. It can't be exposed in the fire-rated exit corridors, but it can probably be installed if it's not exposed in that corridor. The word exposed is need to kind of think through that a little. Can't be in air ducts or return plenums. The standard says also, this is standard 15.2, again for the residential pipe shaft. You need to have pipe shaft if it penetrates 2 or more floor assemblies. Then you need to have a fire resistance rated shaft required by the building code. And if you have that shaft, it needs to be naturally or mechanically ventilated, and the sizes and how much CFM and openings and all that is described in the standard. And that is the way it is now. I wouldn't be surprised if they change that requirement soon, but I'm coming back to that in a few slides. So that is standard 15.2. Now we're going to go back to standard 15, the non-residential, and do the same thing, walk through there and the most important parts in standard 15. Similar here, we're going to determine the charge. We've already done that. We're going to determine occupancy classification. That's a new thing. And then the effective dispersal volume, that is the room volume we kind of looked at earlier, but I will call it something different. We're also going to look at the EDVC, effective dispersal volume charge. That is the M max, the max value. Now they call it EDVC, even though it is more or less the same as what we called M max in standard 15.2. And the same there, we comply if we are below the max values. We already discussed MS and MREL. This is a non-residential, so it could be more likely that we use shut-off valves than we would use MREL, which is the releasable charge, and that would be a part of that system. Occupancy classification. Residential occupancy is something that has complete living facilities. They give examples of dormitories, hotels, multi-unit apartments, and even private residences. That is residential occupancy. Important in this case is institutional occupancy. That is defined as occupants cannot readily leave without assistance of others. Examples are hospitals, nursing homes, asylums, and spaces containing locked cells. Important here is that if there is an institutional occupancy, all the limits have to be 50% of what they are for other occupancies. So it's much stricter with institutional occupancy. I listed below there the other occupancies. They have public, commercial, large mercantile, industrial, and mixed occupancy. And for the purpose of this presentation, we're going to ignore those, but when it comes to the maximum refrigerant charge, residential, or if it's institutional, it's going to be 50% of the numbers. So let's look at how you determine the dispersal volume, the room volume for this. Again, we're going to look at the smallest room where it can disperse or leak. Second bullet, they define a room by walls, ceilings, windows, and doors that can be closed, and partitions above 5.5 feet above the floor. So that means that if you have a cubicle environment that have tall, more than 5.5 feet walls, and the door that can be closed, then that cubicle is a room by definition. If you don't have a door, you're good. Or if you have low partitions, you're good. But that is something to think about when it comes to non-residential. The last bullet is very interesting too. They say that areas with continuous refrigerant piping or joints that have been tested in accordance with local codes, they are exempt from the calculation there when it comes to room volume. And that they're basically saying that if you have put in base door or mechanical connection in the piping and it's tested, it cannot leak. It's going to be a straight pipe. And that's an important thing, that you test it according to the standard or local codes, then you are good from leak, at least in the view of this standard for that. So let's continue to look at the volume for this room. Standard 15, the non-residential says we can have connected spaces with a natural opening. And they say that it has to be maximum 12 inches from the floor, that opening. And we talk about net-free area. So suddenly here in standard 15, they're saying you can have door undercuts. If you look at the left there, I have a 2 foot, I put in a 2 square feet opening. It's below 1 foot high. Then I can use that area to, that is defined as a natural opening. So that could be a really big door undercut. It can be used, it could be even less, obviously. If you have twice the size in the middle there, case number 2, if I have a 4 square feet area, but half of it sticks up about 1 foot, we can only use half of it. The efficient area would be 2 square feet. Or if I have a big opening above that 1 foot limit, can't include it. That's not an opening, and for natural ventilation. So that's how they define this natural opening. And that could be a way to connect 2 rooms, for example, or several rooms. The way to determine that opening is that formula I mentioned on the jungle picture. It kind of looks a little intimidating first, but it's not actually. Let's look at the left there on the yellow. That is a vent, that's the area we are going to calculate. MREL, that's a releasable refrigerant charge. And that is the system charge, we already have that. MROOM is the maximum charge for the smallest of the rooms that this opening is going to serve. So it's kind of straightforward. A is the actual area of that individual room, the smallest room again. So those in the yellow there aren't that tricky, to be quite honest. On the right, we have factors. They are just constants. LFL is the lower flammability limit. It's 19 pounds for R32. MA is just a factor, 29. MR depends on the refrigerant, also a factor. G is gravity, and then there is a conversion factor of 0.417. So it's relatively easy if you get these numbers, put it in an Excel or something, and calculate the size, the net area, minimum net area of that natural opening. The standard also talks about connected spaces with ducted air distribution system. It's kind of generic. It says that you need to look at the whole system, analyze the whole system, and look at worst case scenario if there is a leak. It also says that you can include floor plenums and ceilings if they are a part of the air distribution system. We saw that earlier on that slide with those with the lay-in ceiling. Supply and return transfer ducts shall be included, the volume of those as well, when we look at the room volume. If you have mechanical ventilation, it's similar. Transfer ductwork shall be included when you determine that VEFF, the volume of that room. So now we have looked at how you determine VEFF. The standard has two formulas, two basic formulas. Let's look at the left one. It says that systems with air circulation, heat pump systems with air circulation, use that formula, EDVC. That's the effective dispersal volume charge, the maximum. VEFF is the dispersal volume. We have defined that on the previous slides, the room volume. And then LFL, that's the flammability limit. CF, concentration factor, 0.5 by default. And then FOCC, that's that occupancy adjustment factor. It's 1. Unless it's institutional, then it's 0.5. So it's a relatively simple multiplication there. When we have the volume, we multiply with 3 factors, and then we see the maximum allowed. So that is for system with air circulation. Then the standard says that anything else, other refrigeration systems, we use another formula, kind of similar, but there are a few differences. So we looked at the heat pump with air circulation. If you don't have that, you use the other formula. Calculate the EDVC the same way, MDEF, that is from a table. We're going to look at that. And then the factor FLFL and FOCC, that's those 2 factors we looked at earlier. Now we call it F, they call it FLFL. That factor is slightly different, so we have to take it from a table. So let's look at those tables that we would use to do that multiplication. So now I'm looking at other refrigeration systems. I'm trying to find the MDEF for that formula. I look in the table there, I go down on the left in floor area in square feet. I picked 150, it goes to 10,000, I think, but I picked something reasonable there. For 150 square feet, I can go out to the right and stop in red. That is for 7.2 feet dispersal height. As you can see there in the horizontal top, it goes between 2 and 9. Can't have any other heights in this for this. Same thing here, you interpolate or use closest lower value. So I picked 150 as an example, go out there to 7.2 feet, and that is 10.3 pounds. And that dispersal height, you can see in the lower part there, that is, the height is the lowest point of any opening in the supply air duct, the return air duct, or the equipment providing air circulation. So that's how they define that height number you're going to use in that table. On the right, we can see the LFL conversion factor. You see that table, I think you recognize the one for R32 and 454B has 0.96. It's the same table we saw a bunch of slides ago. They just call it something else here. Unfortunately, standard 15, call it something else, but it's the same kind of table we looked at earlier. So that was systems without ventilation. This standard talks about EDVC without ventilation. We looked at with and without circulation. Now, if you have ventilation, it's kind of straightforward. If you have ventilation, there is an additional factor, an additional EDVC that you can get from a table there. It's a lot of information, so I took out the cool stuff. In blue there, if you have 100 CFM in that table, you get 3.8 pounds extra. Because of that ventilation you can add that to the maximum value you calculated earlier. And then it's just a straight calculation. So if you have 1,000 CFM, it's going to be 10 times more. If you have 4,000 CFM, it's going to be 40 times more than what you had at 1,000 CFM. And so it's very useful table to see how much ventilation you might want to need to comply with the standard. And this is a footnote there. It is for R32. It doesn't say what you do if you don't have R32, but I would use multiply with 0.96 if I have 454B, for example. So that is how we determine the EDVC with out ventilation first, and then we add this for ventilation. Let's see if we comply. So without ventilation, we use those formulas and we can calculate the maximum value, the EDVC. And then we already know the system charge, MS or MRL, and we can compare those two. And then we have to, if we have ventilation, we in yellow there put in, you need to include the value, the extra value you get for ventilation when you look into the maximum for those. So, so that is the charge. That's a way to look at the charge. The standard says, standard 15 says, if the maximum amount is exceeded, do a machinery room. And if some of you have looked into machinery room, you know it is can be very complicated. There are several pages defining a machinery room. They talk about how you use the space, sizes, clearances, doors. Can you have doors? Yeah, but they need to open outward, airflow control, access restriction, refrigerant detection, ventilation. They need to have audible and visible alarms, both inside and outside of that room, manual reset, and it's a lot of requirements for machinery room. So if at all possible, I would try to design to not have a machinery room. People have done it. I talked to people that have done it, and it can be done. It's just going to cost more and be more complicated. So that's the comment about machinery room. Let's look at the RDS, the refrigerant detection system. Do we need that or not? Well, it's a little different here for standard 15. If we have more than 4 pounds and any duct opening is less than 5.9 feet above the floor, we do need an RDS. And also if we use several rooms, ducted rooms together, we need that. We can also need, as we saw earlier, we can need RDS if we need to activate shut-off valves, air circulation, or ventilation. On top of that, we always need RDS if we have institutional occupancy. By default, you need that for institutional occupancy. And RDS in standard 15 has to meet the same requirements. I'm not going to go through all these again, but they are almost exactly the same as for standard 15. That is what the RDS need to comply with. Similar here, if you have a leak, you're going to activate fans and shut off resistance heat, etc. The only difference here in this standard is that you need to de-energize ignition sources bigger than 1 kVA or open flames. So piping requirements. Let's look at piping requirements. This is similar to standard 15.2. The requirements, the word exposed, passageways, etc., 7 foot 3 inches height. The big difference could be the refrigerant shaft. Until recently, it said that if you have 2 or more floor assemblies, you need to have a fire-resistant rated shaft. That's for standard 15. But that's changed. They came out with an agenda. This is good news for so many of us. in May, end of May this year, they came out with an addenda saying you don't need shafts in standard 15. Standard 15.2, you do need them still. Standard 15, you don't need them. So at the addenda, with this little paragraph or this little section in that addenda, they changed a lot of things in standard 15. They're basically saying you don't need a shaft if you have continuous piping or tubing that has been tested in accordance with section 913. Then they're basically saying that we discussed earlier, if it's a straight pipe that has been tested, it cannot leak. And that can be a big difference. So at the end here, we're going to look at what you do if you don't comply. Well, if you don't comply, you are above a limit, whether it's EDVC or Mmax. And to me, it's like a balance between the room volume and the charge. That's not proper if you don't comply. And there are ways, if you look at the left, there are ways to kind of increase the room volume. You can have automatic or even automatic air circulation, can remove or raise that suspended ceiling we looked at, move a fan coil, or perhaps duct it to multiple rooms, put in the refrigerant detector, the detector, they will combine room volumes. We saw that on one slide too. Or we can add or enlarge that opening between the rooms. And we saw how we calculated that, or we could have put in that door passageway. Add ventilation for dilution. We also saw the factors that how much you can gain if you have ventilation. Or you can also move indoor units or supply ducts, put them higher in the room. Then the height is going to be higher. That number is going to be higher. You're going to allow more refrigerant. You can also decrease the refrigerant charge. Put in those shut-off valves. That's going to decrease it. How much can leak? You can move or perhaps even remove an indoor unit. Move some piping. Good to do. And then that's when that software design simulator is perfect. You move something and you can immediately see if it helps you, how much it helps you. You can do a what-if scenario. Split the system into multiple smaller systems. It can be a good idea, especially if you have a VRF system of a certain size. Instead of a 40-ton, you can have two 20-ton systems, and it doesn't have to be much more expensive because it's the same kind of equipment. It's just that the commissioning can take a day extra or something. You can replace some fan coils or put in mini splits in a part of that building. I've seen several cases where at the end of a building with many rooms, they were above the limit. Well, let's take out a couple of the rooms from the big system, put in mini splits there, and then we comply. You can also use ducted zoning system for several zones. So this was just a kind of a quick hint on what can be done if we don't comply, unless we want to do the machinery room. So the takeaway, to me, heat pump systems can with A2L can be in almost all cases, in all applications. We saw that institutional occupancy could be a challenge. There are ways to design around that too, but the 0.5 there, multiply the maximum amount with 0.5 could be a limiting factor. We also need to remember that they are design guides. These standards, there's engineering judgment that should be applied there. There are ways to design smart, design around this. And again, at the end of the day, it is the ASHRAE that sign off on this. So that was my last slide. I have one left. We have a few minutes left. If you want to have this certificate about these PDH credits, as we mentioned earlier, you put it in the chat, and then you can take a look at these questions. I believe that you already know how to answer these. I'm going to just give you 10 seconds to look at them, but we need to have some questions at the end, and in my mind, you all passed it. The first one is answer C. Next one is answer C, and the third one is also answer C. So I think you just passed it. Thank you.
It really didn't switch up there, Lennart. That's funny. Hey, so we were having some feedback that the chat wasn't working. So if you do want a PDH credit, you need to send it to us in the form of a question. But that said, we actually are taking questions right now. and we have a couple, Lennart. So one of the questions was in regards to slides 22 and 23. Why doesn't a door with a transfer grill count, but a transfer grill to the plenum does?
I agree. It is, I can't answer, to be honest. It's a lot of things in this standard. I don't understand it. I really don't. Even though I'm an engineer and, looked into it, they're just saying you can't have a door undercut. You can't have it. So, and that's a challenge here, because you can't use a part of standard 15 and the part of standard 15.2. But you could take, let's say you have a 10-story building and you have stores or some shops in the lower part, that would probably be standard 15, but the upper part of that building would be 15.2 if you have apartments there. But I can't answer it. The standard is confusing.
Yeah, so basically, I think that the key here is the difference between 15 and 15.2, right?
Yeah. And it's they are not consistent. To me, it was two groups that wrote them separately, and they met a couple of times, and then they were done, because it should be much better coordinated. I see some effort to do that in some of the addendas they came out with during the spring here, but it's still inconsistent, unfortunately.
Yeah. So here's another question. So if all piping on the project is brazed and tested, is the project exempted entirely from these new requirements? If not, which requirements still apply? And that was at 1236. So I think that was before you addressed the ASHRAE 15 chase requirements. So go ahead.
I hope so. And I can add, I think I answered that, but it's a good question, because the standard says that you should test these, pressure test and all that according to the standard or manufacturer's specifications, test specifications, and you should use the one most stringent of the standard testing or the manufacturer's testing. But when you do that, then it's considered to be a straight pipe that can't leak.
Great. So if you have any other questions, please feel free to throw them in now. Richard, are you still on the line?
I am. There's a new question that came in. It asks, does ASHRAE 15 limit the use of copper line sets?
Yeah. No, it doesn't. It's specified also there in several pages, but it's actually, compared to the previous standard 15, it is a little more easier now but no, you specify what kind of copper and sizes and stuff, several pages, but no, there's no.
Yeah, so that kind of concludes. Oh, we got one more question. How common are the safety shutoff valves? About 7 years ago, I tried to use a similar approach, and I could not find solenoid valves that accommodated reversing flow.
They are going to be very common because of the standard, and we already have them for the mini splits, and we are going to have them very soon when we launch the R32 VRF system.
Good question. So, here we go. Yeah, so I've been getting a lot of questions about the slides. So first of all, we did this presentation at ASHRAE 2 weeks ago, and those slides were uploaded to the ASHRAE website. But at the same time, we are going to send these slides directly to you in a follow-up email. And in that email, we'll probably include some other documentation about some of the stuff you see on the screen right here, actually, about how to access the system layout, how to access the system selection program, which is available to anybody. The program you see at the top right there, that layout, it's really easy to use, very intuitive, and it's the same program that Fujitsu uses, the same program that the reps use, and the engineers and even the contractors that they want it. So you can have access to that. We'll show you how you get that. We'll also send you a detail that you can use in your plans that would that list these condenser supports and platforms. Typically, you guys are probably pretty familiar with the quick slings and the Bigfoots out there that are used to mount these condensing units. And what Buckley has done is come up with these kind of like a modified equipment support and curb in which it's actually a lot more economical and easy to install. It's just like a preferred method of mounting these condensing units that we've seen a lot. Like I said, faster to install. They're less expensive, and they're built right here in New England. So getting them on site already assembled is a huge bonus too. So there's those. We also make pipe portals of any size that you need, and that represents a really good method of mounting that the contractors like. And finally, those filter boxes. We've actually been making those filter boxes for a lot of different VRF manufacturers for a while now. For about 10 years, we've been making these out of the New England manufacturing plant at Buckley. So definitely worth considering using those on your projects as well. But that said, I just want to highlight again that Buckley is very invested in this VRF market. It's something that we've had a lot of success with since introducing Fujitsu as a line a little over a year ago. I know Richard Glatt here is really excited about the work that we've done, and we have a lot of support on the street. We have our whole service team that can support this, start it up, and help that way. We also train contractors and give them certifications that bring some warranty benefits, and it's just worth thinking of Buckley as a resource here, and we have a lot we can share with you. And Richard, do you want to, this is at this point the PDH is over, but if you guys want to see what we have coming, it'd be worth maybe just seeing what our roadmap ahead looks like. I know that we have Richard, you want to share that really quick?
I can. There was a few more questions that came in the last few minutes. If you want to.
Yeah, why don't you work on pulling it up, and then I'll address these questions. Let's see.
Okay.
Do you have any sample designs to show? We've done a ton of designs. Roy, if this is something that we could talk about offline, that would be great actually, because we have, like I said, we have a whole department that kind of works on this stuff, and we actually have a pretty great install list since bringing Fujitsu in, so we could talk about really anything. If R424 and R32 are very similar in most regards except ignition temperature, why would I pick one over the other? I hate to say this, but you might be talking about R454B versus R32. There is a reason to go to R454B over R30. Sorry, go to R32 over R454B, which was kind of highlighted through the presentation. And one of those is that R32 is a single source. You only have one refrigerant, as opposed to it R454B being a mix. There's also some other benefits to that too. But Lennart, you want to mention that? And by the way, whoever's sharing the screen, you have a lot going on here. Rich, is this you?
Yeah. Do you not see my R32 roadmap?
No, I don't.
Okay, let me stop sharing. Is that better?
Well, we don't see your roadmap yet, but Lennart, do you have anything to add to that about R454B versus R32?
I can. I gave a webinar about that a year ago or so, but we Fujitsu picked R32 because we have a lot of experience with that outside US. We had it for almost 10 years. And you will see that now in availability and pricing also, but it's a few percent more efficient than 454B. That's the most common right now. It's also going to be less refrigerant charge in the system if you have R32. And it is a couple more things that really made it easy for us to do it. And we have seen the availability of 454B is limited. Interesting though is that the other blends, R32 is not a blend, but the other blends have one refrigerant called R1234YF, and that is only coming from one manufacturer. So that blend, those blends have one component that's coming from one manufacturer only, and that's typically not good if something is coming from just one manufacturer.
They have control of pricing.
The pricing, availability, and a lot of things.
Well, there's one more question about fireproof shafts, and I just want to address that. ASHRAE 15.2 is very clear that you do need a fire-rated shaft. either naturally ventilated or mechanically ventilated. But ASHRAE 15, as I just want to highlight that ASHRAE 15, as of May 30th of 2025, earlier this year, they eliminated that from ASHRAE 15. So on a multifamily building, there's actually a way that you can apply both standards to that multifamily building. The ASHRAE 15.2 applies to the apartments, while ASHRAE 15 applies to the shared common areas. So I think there's a way to kind of manipulate that, right, Lennart?
Yeah, you're right. You do it smart. You really can.
All right, so that please feel free to ask more questions, but let's go to this roadmap just so you guys can see where Fujitsu is at with bringing the A2L refrigerant to the market.
You see the screen now, Matt?
Yeah, we see it.
Okay, perfect. So just as a heads up, right, we're just gonna look at VRF. We already have the R32 product offering. About 95% of those products are already here in the US. We've been selling them all year through 2025. We have a few products still hitting the warehouse the last part of the year, but moving forward, we've also started with our first of the year, our J7S, which is our single phase 2, 3, and 4 ton single phase heat pump mini VRF product with a limited indoor unit lineup as well. And then what we're looking at here on the roadmap is going to be what's coming in the first part of the year. And I'll sort of show at the last slide, I've only got a couple slides, the time frame on that. So we're going to have our 3, 4, and 5 ton, which is also our mini VRF. We're going to have two different versions, our J7S as well as our J7. The J7S that we currently have is 2, 3, and 4 tons. This will be our J7. That'll be 3, 4, and 5 tons. Again, single phase heat pump that will be coming soon, as well as our VU7, which will replace our current VU5 offering. And this will be our 3-phase commercial 208, 230 3-phase, as well as 460 volt from 6 tons up to 32 tons. So our largest will be 32 tons with a dual module chassis piped together in the field. And again, that should be up to 16 tons in a single module. Okay, so 2 modules piped together to make 32 tons. Indoor units, this is a little bit of a busy slide, but the highlight here is, this is the overall view. The highlight is every one of our new VRF indoor units that we'll have for R32 coming in next year in a few months will include a built-in refrigerant leak detection sensor. The current models that we have for the J7S, it's only the ducted models that include it. Whereas moving forward, our ducted as well as ductless, including wall mounts and ceiling cassettes, will already have a built-in leak detection sensor. So that should make designs a little bit easier as well. And again, the footprint that we show on the screen here is very similar to what we have today in R410A. And there are a few models that won't come out until later next year, especially the floor mounted model, because it's very different how they apply to the standard, because the unit sits so low on the wall or close to the floor. So that's kind of what we have. And the roadmap will be the VU7 and the indoor units will be January production, which would hit our warehouses here in the US, say March, April timeframe. These, of course, are manufactured overseas. The J7, that 3, 4, 5 ton is March production, which should make its way to our warehouses in the summer. So June, July timeframe. And also the VU7 that comes out March, April timeframe will include single port as well as 4-port heat recovery boxes. We call them RBU boxes. And then our 8 and 12 port RBU boxes won't be into production until June. So we won't have those out here in the US until maybe August, September timeframe. So that's kind of how it's going to lay out. Thought I had one more thing to say, but maybe I forgot it. So
it's all good. That was
yeah,
good. Thanks for the update.
Yeah.
But that, I mean, honestly though, that pairs well with the timeline that Lennart showed earlier. You know, with the install requirements for A2L versus the R410A.
Yeah, and that being said, that's for the equipment. I don't have a firm timeline on when we're going to have product data, design tech manuals, have the new equipment in our design simulator software. That should be happening in the next few months between now and about the end of the calendar year. So again, stay close with Matt and the team at Buckley, so we can get you that material as soon as we have it available, and you can have some data to start working on your designs. We appreciate your patience.
Yeah, exactly. So just keep me updated if you guys have any projects. You know, anybody at Buckley that you work with will be able to tap into our VRF resources. So if you have any questions on a project that you currently have going on, we'd love to help you out. Just let us know, and we can get that going. So like I said, we're going to send a follow-up email to this with all the slides. But oh, one more big thing I probably didn't mention. This presentation actually will be on our website, on our training portal. So if you had a coworker, colleague that missed it, feel free to share that with them as well. Thanks everybody for coming. Thanks Lennart and Rich.
Thank
Thanks
you.
for hosting.